More than 200 kilometers of entirely new metro lines, 68 underground stations, and nearly 20 giant tunnel boring machines are operating simultaneously beneath the heart of Paris, one of the most complex cities in Europe. Right below historic boulevards that are over a century old, France is building a completely new underground transport network, large enough to be considered a second metro city, forming in parallel with the Paris we see today. After more than 120 years of operation, the original metro system, designed for a previous century, is becoming the biggest bottleneck for a metropolitan region of over 12 million residents. So how can such a massive metro network be constructed beneath one of the most complex urban environments in Europe? Let's explore the answer together with Mandarin Tech. Grand Paris Express is an entirely new transport network being built almost from scratch beneath the Paris metropolitan region. When completed around 2030, the system will include 4 fully automated lines: lines 15, 16, 17, and 18. To make this network possible, dozens of deep construction shafts have been opened right in the middle of existing residential areas, allowing a large number of tunnel boring machines to operate simultaneously underground. At the same time, around 600,000 precast concrete segments are being continuously manufactured to form the protective lining of the entire new tunnel system. Many of the stations are being built at depths comparable to multi-story buildings and will connect directly with the existing metro and RER networks, creating a completely new cross-regional transport structure. Once in operation, the network is expected to serve around 2 million passengers every day, making Grand Paris Express the first major orbital transport backbone that allows suburban areas around Paris to connect directly with one another, without having to pass through the city center, as commuters have been forced to do for more than a century. Before the first tunnel boring machine even began to rotate, Grand Paris Express had already become one of the most complex infrastructure preparation campaigns ever carried out in Europe. Unlike metro projects built in undeveloped areas, most of the new lines had to pass through urban districts that have existed for hundreds of years. This meant that before digging underground could begin, the entire surface environment above had to be reorganized. Hundreds of land parcels were acquired. Many existing structures had to be demolished. Several roads and utility systems were temporarily relocated to make space for construction shafts. In the Arc-à-Cachan area, to prepare the connection between the new metro line and the existing RER network, a massive steel structure weighing about 3,000 tons was pre-assembled and then slid sideways nearly 26 meters in just a few hours. This marked the starting point of one of the largest underground construction operations ever deployed in a densely populated urban environment. If the tunnels are the structural backbone of the Grand Paris Express, then the stations are the strategic anchor points that determine how efficiently the entire system operates. Most of the Grand Paris Express stations are built using a controlled cut-and-cover construction method. First, engineers construct reinforced concrete diaphragm walls around the perimeter of each future station site. Deep trenches are excavated in advance, steel reinforcement cages are lowered into place, and concrete is poured to form a stable structural frame that protects the entire construction zone. Only after this protective box is completed can the soil inside be excavated layer by layer in a carefully planned sequence. Alongside structural requirements, engineers also had to solve another critical challenge: minimizing transfer time between lines. For this reason, both the location and elevation of each station are designed to keep connection distances to existing metro and RER lines as short as possible. Tunnel boring machines, or TBMs, are the primary force responsible for creating the entire underground tunnel network of the Grand Paris Express. In this project, more than 20 giant TBMs operate simultaneously beneath the city of Paris, forming one of the largest underground construction campaigns ever carried out in a dense urban environment. Each TBM is about 100 meters long, with a cutter head nearly 10 meters in diameter. This is not just a drilling machine. It is essentially a mobile underground factory capable of excavating soil, transporting materials, and installing tunnel lining segments directly behind the cutter head in one continuous working cycle. At the front of the TBM is the massive cutter head, which breaks through the soil and rock ahead of the tunnel path. Depending on the geological conditions, the cutter head is equipped with different tools, ranging from scraping blades designed for soft ground to heavy-duty disc cutters used for harder rock layers. Although the cutter head is extremely large, it rotates quite slowly, usually only a few revolutions per minute. However, the force it generates is enormous, powerful enough to break through geological layers located dozens of meters below the surface. Once the ground is excavated, the material is transported backward through a giant screw conveyor system, then transferred onto conveyor belts running along the body of the machine to carry it out of the tunnel. This entire process operates continuously, turning the TBM into a fully integrated construction system that can advance forward meter by meter while still maintaining safety for the dense urban environment above. Right behind the tunnel boring machines, the concrete lining of the tunnel must be installed continuously to ensure the long-term stability of the entire structure. This lining is made up of precast reinforced concrete segments known as voussoirs. Across the entire Grand Paris Express network, about 600,000 of these segments will be produced to form the protective structure for more than 170 kilometers of underground tunnels. Each segment weighs between 4 and 9 tons, and 7 segments are assembled together to create one complete tunnel ring. The production process begins with cleaning the molds and applying a release agent to ensure the segments can be removed easily after curing. Next, waterproof gaskets are precisely installed inside the molds to guarantee the watertight performance of the tunnel rings once assembled. After that, the reinforcement cage is placed into the mold, forming the main load-bearing framework of each segment. Once all components are in position, concrete is poured into the mold and compacted using pneumatic vibration equipment to ensure an even distribution throughout the entire volume. The molds are then moved into curing chambers, where temperature and humidity are carefully controlled to accelerate the hardening process. After only a few hours, the segments can be removed from the molds and transferred to the storage area. Thanks to this continuous production system, a new concrete segment is completed roughly every 10 minutes, fast enough to keep pace with the excavation progress of multiple underground construction fronts operating simultaneously beneath Paris. It is the multifunctional tunnel boring machine itself that turns individual concrete segments into a precisely engineered geometric structure running deep beneath the city of Paris. Each segment is lifted into position by robotic arms and installed according to a carefully calculated sequence. Once the tunnel ring is closed, the machine uses this newly installed concrete ring as a reaction surface to push its entire body forward by about 2 meters. However, the real challenge is not simply creating straight tunnels. Paris is a layered maze of infrastructure: ancient foundations, older metro lines, sewer networks, and historic structures. To avoid these obstacles, the tunnels of the Grand Paris Express must constantly change direction as they move through the underground environment. This is achieved by carefully adjusting the geometry of each segment ring. With only very small changes in the installation angle between the concrete segments, the TBM can create large radius curves while still maintaining watertight performance and structural stability. Thanks to this technique, the tunnel alignments can curve precisely beneath the city without affecting the structures above the surface. In fact, beneath Paris lies an extremely complex underground environment that has developed over many centuries. In addition to the existing metro lines and modern technical infrastructure, this area also contains numerous old limestone quarries and natural voids that could create subsidence risks if they are not treated before construction begins. Before tunneling machines pass through these areas, engineers must first inject grout into the underground cavities to stabilize the soil. This process is carried out by drilling small boreholes from the surface down to the zones that need reinforcement, then pumping liquid material into the voids to completely fill the empty spaces. However, for a project stretching across hundreds of kilometers, like the Grand Paris Express, engineers deployed a terrain deformation monitoring system based on radar satellites, one of the most advanced monitoring technologies ever applied to an urban infrastructure project. Approximately every 11 days, the TerraSAR-X satellite passes over the project area along the same orbital path and sends radar signals toward the Earth's surface. Thanks to this radar interferometry technology, tens of thousands of measurement points per square kilometer can be monitored simultaneously throughout construction. This allows engineers to detect even the smallest ground deformations early and adjust construction activities before they develop into real risks. Within the entire Grand Paris Express network, Saint-Maur Créteil station is the deepest station ever built in France's underground transport system. Located about 52 meters below ground level, roughly equivalent to the height of an 18-story building. Constructing a station at such a depth created a major challenge for passenger accessibility. How could people move quickly between street level and platforms located more than 50 meters underground? The solution was a system of 11 high-speed elevators capable of transporting passengers to this depth in about 15 seconds, making it one of the fastest vertical access systems in the modern French metro network. The station structure itself is also highly unusual. Instead of the traditional rectangular layout, Saint-Maur Créteil was designed with a dual parallel chamber configuration shaped like a peanut, which helps optimize construction space in complex geological conditions, while also distributing loads more efficiently along the tunnel walls. These engineering challenges clearly demonstrate how designers had to adapt to some of the most demanding underground conditions beneath Paris in order to build a completely new metro network for the 21st century. But at this point, you may be wondering what actually led to the creation of the Grand Paris Express. To understand that, we need to go back to 1900, the year when Paris opened its very first metro line. At that time, the underground network was designed with a very clear logic: to bring passengers into the city center. The metro lines functioned like spokes converging toward the historic urban core, where most of France's population, jobs, and economic activity were concentrated. For many decades, this structure worked efficiently, but by the end of the 20th century, Paris had changed completely. Millions of people began living in the suburbs, while research centers, airports, universities, and new economic zones were spreading across the wider Île-de-France region. As a result, the historic urban core gradually became a major bottleneck for a metropolitan area of more than 12 million residents. In fact, the idea of building an outer orbital metro network had already been proposed by earlier generations of planners. However, the enormous cost and shifting urban planning priorities caused the project to be delayed repeatedly. It was only in the early 21st century, when transportation pressure reached its limits and Paris urgently needed an entirely new connectivity structure, that the plan was finally revived. When completed, the Grand Paris Express network is expected to serve around 2 million passengers each day, creating direct rail links between suburban districts that once depended heavily on private cars. By shortening travel times across the Île-de-France region, the system will not only ease congestion in central Paris, but also significantly reduce transport-related emissions across the wider metropolitan area. At the same time, the project is transforming the urban landscape far beyond the tunnels themselves. Dozens of new districts are being planned around future stations, turning previously disconnected areas into emerging hubs for housing, universities, research centers, and business activity. These developments follow a high-density yet environmentally conscious planning model designed to support long-term regional growth. Even the massive volume of excavated material, about 45 million tons of soil removed during tunneling, is being reused for land reclamation, infrastructure platforms, and landscape restoration projects, ensuring that much of what was taken from beneath Paris is returned to shape its future surface. Grand Paris Express is not just a new metro project beneath Paris. It is one of the largest urban infrastructure restructuring efforts in Europe in the 21st century. With more than 200 kilometers of tunnels and dozens of completely new stations, this network is quietly changing how over 12 million people travel every day. This is how a city more than a century old is rebuilding itself, not on the surface, but tens of meters underground. When the Grand Paris Express is completed, Paris will not simply gain another metro line. the city will gain an entirely new transportation structure designed for the next century.